Okay, so let us start today's session. Actually, from 1 to 20 questions we have done in our first and second session. Now, this is third lecture of D and F block elements. We are doing this D and F block elements through question and answer. And question is, what is lanthanoid contraction? And write consequences of lanthanoid contraction. This question we have already covered, but today we will do it once again. So Pranay, tell me, what is lanthanoid contraction? What is lanthanoid contraction? Pranay, what do you mean by lanthanoid contraction? Hello, we have already done it. Yes. So if we write it in a complete sentence, it is the regular decrease or we can say contraction. Contraction means decrease. So regular decrease in the atomic and ionic radii of lanthanoids with increasing atomic number. Is known as lanthanoid contraction. So this is the definition. Yes, Shri, did you understand that regular decrease in size of is atomic or ionic radii of lanthanoids, that is called lanthanoid contraction. Now, lanthanides are from cerium to lutetium, but because lanthanum has almost similar properties to lanthanoids, that is also included in it, and different lanthanoids are starting from lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, dysprosium. Sorry, before dysprosium there is terbium. Yes, gadolinium, then terbium, then dysprosium, holmium, erbium, thulium, ytterbium, and at the end it is lutetium. So these are the lanthanoids. These are the lanthanoids. So when we say along the series, that is as the atomic number increases, their size decreases. Means if you plot a graph between atomic or ionic radii versus atomic number, then graph is like this. And there is a steady decrease. Okay, This is lanthanum. Most common oxidation state of lanthanoid is +3. So lanthanum 3 plus, cerium 3 plus, then praseodymium 3 plus, praseodymium, then neodymium, samarium. Okay, before that it is promethium. Yes, promethium. You have to remember the series: promethium, samarium, europium, then gadolinium, terbium. Then after terbium there is dysprosium, then holmium, thulium, thulium, I think it is erbium, yes, erbium, then thulium, ytterbium, and at the end there is lutetium. So in this way there is a decrease in ionic radius, and this is called lanthanoid contraction. Okay, this steady decrease or regular decrease in the atomic and ionic radii of lanthanoids with increasing atomic number is known as lanthanoid contraction. Now, what is cause of lanthanoid contraction? Yes, beta. What is the cause of lanthanoid contraction? Yes. Very good. It is the cause of lanthanoid contraction is it is due to imperfect shielding of 4f electron, one 4f electron by another 4f electron of the same subshell. Okay, so shielding of one 4f electron by another, and it is less, and that's why there is a steady decrease in size. So you can write it is due to imperfect shielding of one 4f electron by another 4f electron. Now come to the consequences. Now consequences of lanthanoid contraction. So first consequence is difficulty in separation. Difficulty in separation of lanthanoids. So what is the reason? Because the change in radius in lanthanoid is very small. I said there is a steady decrease, regular decrease, but very, very less. So due to this steady decrease, the size of the size difference among lanthanoid is very, very small. Size difference among lanthanoids. जी कोई बात नहीं ठीक तो size difference Among lanthanoids, it is very small. Okay, therefore, their chemical properties are similar. Okay, what I said, there is a change in ionic radius in lanthanoid, but that change is very small. So size difference among lanthanoid is very small, and therefore their chemical properties are almost similar, and that's why it is difficult to separate them in pure state. Okay, so because of similar chemical properties, this makes the separation of lanthanoids in the pure state difficult. This makes the separation of lanthanoids in the pure state difficult. Okay, so they can be separated by ion exchange method, but that is very difficult to separate. So this is the first consequence of Lanthanoid contraction. Second is similarity in size of elements belonging to same group of second and third transition series. Okay, so as we go down the group, generally size of the atoms increases, but size of the atoms of any element lying in the second transition series, it is larger than that of the atoms lying in the same group of the first transition series. That is expected, but size of any atom of the third transition series is nearly same as that of the element lying in the same group of the second transition series. For example, zirconium. Above zirconium there is titanium, and below it is hafnium. Atomic number of titanium is 22, zirconium 40, and hafnium 72. So see, from titanium to zirconium there is an increase in size, but from zirconium to hafnium they have almost same size, and reason is very simple, due to lanthanoid contraction, due to the presence of extra 14 f electrons. Because see, from 22 to 18, 22 to 14, there is increase in 18 protons. But from zirconium to hafnium, there is an increase of 32 nuclear charge, means extra 14 f electrons. And due to presence of those 14 extra f electrons, which have imperfect shielding, effect of nuclear charge is more, and that's why effect of extra shell is less. Effect of the extra shell is less, and that's why zirconium and hafnium have almost same size. Although hafnium has very little smaller than zirconium, but almost same size. If question, many times there is a question that why zirconium and hafnium have almost same size. So you should write it is due to lanthanoid contraction. Same yttrium, niobium and tantalum. So niobium and tantalum, they have almost same size. Though yttrium has smaller size than niobium, but niobium and tantalum, they have almost same size. So these elements belong to second transition series and these elements belong to third transition series. So elements belonging to the same group of the second and third transition series, they have almost same size, and it is due to the effect of lanthanoid contraction. It is due to the effect of lanthanoid contraction. Third consequence is effect on the basic strength of hydroxides. Effect on the basic strength of hydroxides. So say as the size of the lanthanoid ion decreases, see size of the lanthanoid ion decreases as atomic number increases from lanthanum 3 plus to lutetium 3 plus. There is a decrease in ionic radius. There is a decrease in ionic radius, and that's why, you know, covalent character of their hydroxides increases, because as size decreases, charge density increases, so effective nuclear charge increases, and hence the basic strength and hence the basic strength decreases. So that means lanthanum hydroxide and lutetium hydroxide, if we compare them, lanthanum has largest size, so it is most basic, and lutetium ion has smallest size, so it is least basic. Reason is simple: when metal attached to oxygen is small in size, then MO bond breaking is difficult, because this MO bond is then covalent in nature and it is very difficult to break it, and therefore basic strength decreases. But if metal attached to OH is large in size, this bond is almost ionic and therefore it is easier to break, and therefore its basic strength increases. That is the reason. So what is lanthanoid contraction and what is its consequences and reason for lanthanoid contraction? What is the cause of lanthanoid contraction? That is very important question. Next question. How would you account for the following? That highest oxidation state of transition metal is usually exhibited in its oxides. So highest oxidation state of metal is exhibited in its oxide and or fluorides because of their high electronegativity, low ionization, energy and small size. And why usually oxides and hydroxide? Because of their high electronegativity, and the power of oxygen is superior than fluorine because of its ability to form multiple bonds. Because of the ability of oxygen to form multiple bonds, its ability to oxidize the transition metal to higher oxidation state is more. Okay. Next question. Oxidizing power of the following three oxoanions in the series. Follow the order: VO2 plus, Cr2O7 2 negative, and MnO4 1 negative. By mistake it is written like this. It is VO2 plus, Cr2O7 2 negative, and MnO4 1 negative. So why oxidizing power of 3 oxoanion is in this order? I think this question is not covered in the previous lecture. Yes, Pranay. So this is due to, okay, this is due to this, and this question, okay, sorry, it is VO2 1 plus. Okay, so keep in mind it is VO2 1 plus, that is less than Cr2O7 2 negative than MnO4 negative. So reason is, it is due to the increasing, you will write, this is due to increasing stability of the species with lower oxidation state of the metal in which they are reduced. See, VO2 1 positive, it is reduced to VO2 plus. So in VO2 1 plus, what is the oxidation number of vanadium? X minus 4 equal to plus 1 means here it is in plus 5 state, and in case of VO2 plus, it is in plus 4 state. Now come to next, Cr2O7 2 negative. Tell me, Cr2O7 2 negative is reduced to, yes, Pranay, that you know, Cr3 plus. Just remember, Cr2O7 2 negative is reduced to Cr3 plus. MnO4 negative is reduced to, it is reduced to 2 plus. Mn is reduced to Mn2 plus, MnO4 negative in acidic medium. MnO4 negative is reduced to Mn2 plus. Okay? Remember? We have done this. Okay, because here its oxidation number is plus 6, and in Cr3 plus, oxidation number is plus 3. In MnO4 negative, oxidation number is plus 7, and here it is plus 2. So just write the electronic configuration. Vanadium is atomic number 23, so it is 3d3 4s2. So vanadium in +5 state is 3d0, and vanadium in 4 plus it is 3d1. Chromium 24, its valence electronic configuration is 3d5 4s1. So chromium +6, again 3d0, but chromium 3 plus it is 3d3. Mn 25, it is 3d5 4s2. So Mn +7, it is 3d0, and Mn 2 plus it is 3d5. So this one is exactly half filled. This Cr3 plus is T2J3. I let you know what is T2G and Eg. Here it is T2J and Ag2. So Mn2 plus is more stable than Cr3 plus, and then come to V4 plus because it is only 3d1. So because of the stability of these species, increasing stability of these species with the lower oxidation state of the metal, this is the order of oxidizing nature. Okay. Oxidizing power of the following 3 oxonions in the series follow the order. Why? So you should write the answer that this is due to increasing stability of the species with a lower oxidation state of the metal in which they are reduced. And this is the question, in text question. In D and F block elements, this is an in text question. Next, assign reason for each of the following. First question we have covered in previous lecture. Transition elements exhibit paramagnetic behavior. Tell me why. Yes, Pranay. What is the reason? Paramagnetic behavior. Paramagnetic behavior is due to presence of unpaired E minus means electrons. Presence of unpaired electrons. Okay. So most of the transition elements, you can write most of the transition elements have unpaired electrons in transition elements or their ions. Okay. Have unpaired electron in the D subshell. In we can write n-1 D subshell. In n-1 D subshell, that's why they exhibit paramagnetic behavior, because paramagnetic substances are those which have unpaired electron. Okay, and you know, in most of the transition elements or their ions, they have unpaired electrons, and that's why they exhibit paramagnetic behavior. That's the reason. Okay, cobalt 2 plus, it is easily oxidized to cobalt 2 plus is easily oxidized to cobalt 3 plus in the presence of strong ligand. So strong and weak ligand. Let us I let you know what are strong ligands, what are weak ligands. That is the part of the next chapter actually. But anyhow, D and F and coordination compounds both are interconnected. So few of the concepts of this chapter can be explained if we know that splitting of d orbitals, especially in octahedral field. So as I have explained in the previous lecture, in octahedral field, ligands are where? In octahedral arrangement, or that is also called octahedral field, ligands are, where are the ligands? On the axis or in between the axis? Yes, beta. Ligands are on the axis or in between the axis? Very good. Ligands are on the axis. See, this is taken as z axis, and this one is, next one is, let us say this is x axis and this is y axis. Okay. So now in octahedral field, first of all, right, I am explaining it once again. Ligands are on the axis. Now let's go to the next part, that is shapes of d orbitals. In d subshell, how many d orbitals are there? In d subshells, how many d orbitals are there? Yes, 5. And their shapes are different, like dxy, dyz and dzx. They are of the same type, because in these cases ligand lobes are on the, lobes are in between the axis. Lobes are in between the axis. Because x, y, z, they are perpendicular to each other. So we are showing only two axes. Like in dxy, we need to know x and y axis, because lobes are in between the x and y axis. So we will write it like this. dyz, lobes are in between the y and z axis. dzx, lobes are in between the z and x axis. So in these three, dxy, dyz, dzx, lobes are in between the axis. But in case of dx square minus y square and dz square, lobes are on the axis. So in this way, we come to know that there are 5 d orbitals, but 3 orbitals are those in which lobes are in between the axis, and 2 orbitals, that is dx square minus y square and dz square. In these cases, lobes are on the axis. See, the lobes which are on the axis, see, they are head on to the ligands. See, lobes are on the axis. So those lobes which are on the axis, they are head on to the ligand. So as ligands and lobes, they are ligands and lobes, they are head on to each other. So as they are head on to each other, so their energy is increasing. And other one, dxy, dyz, and dzx. In these cases, lobes are in between the axes, so they are not directly directed towards the ligand. They are away from the ligand. That's why their energy is decreased. See, 2 dx square minus y square dz square. These are called Eg. These orbitals are called Eg. So they are directed towards the ligand. That's why these lobes of the orbitals and ligands, they interact more. And you know, ligands have electrons, lobes are meant for electrons, so they repel more, and that's why their energy increases. But in case of dxy, dyz, and dzx, lobes are in between the axes, therefore they are directed away from the ligands, and therefore their energy decreases. And these three are called T2G in octahedral field. This G word stands for grade. What is grade? That say dxy means x into y. This is x plus direction of x. This is minus direction of x. This is plus direction of y. This is minus direction of y. So plus plus plus, plus minus minus, minus minus plus, plus minus minus. So if we pass a line through the lobes, their sign is not changing. Okay, and as this sign is not changing, so we use G word, grade. So G is for that. If the sign changes, like in P, see PZ. So PZ, it is plus, it is minus. So if we pass a line through it, then what happened? Sign changes. So such orbital are called ungraded. Okay. So d orbitals in octahedral field, they are grade. That's why it is called T2G. T2 means triply degenerate, E matlab doubly degenerate. Okay. So now if we have free ion, if we have free ion, this is free ion. So in free ion, d orbitals, that is dxy, dyz, dzx, dx square minus y square, dz square. They have similar energy, and they are called degenerate orbitals. They have degenerate orbitals. But when ligands are arranged around the metal, this is for free metal or free metal ion. But when ligands are arranged, then what happened? They are separated, means degeneracy is removed. Degeneracy is removed, that is octahedral field, means ligands are arranged octahedrally. So energy of which orbital is more? Tell me. Eg or T2G? Which has higher energy? Yes, beta. Which has higher energy, T2G or Eg? Beta, Eg. Because in Eg, ligands and lobes are head on to each other. Ligands or lobes are head on to each other. So energy of Eg is more, and T2J, their energy is less. Okay, because in T2J lobes are directed away from the ligand, but in Eg lobes are directed towards the ligands. So this is T2G and Eg. Now, what about strong ligand and weak ligand? See, this is for P metal ion. Now, if ligand is strong, the energy difference is more. Energy difference is more. And if ligand is weak, energy difference is less. This is for weak ligand, and this is for strong ligand. If ligand is strong, then energy difference is more. And if ligand is weak, energy difference is less. Now tell me, if arrangement is octahedral, then what is the hybridization? In the octahedral arrangement, that is Ml6, what is the hybridization? What is the hybridization? So keep in mind, hybridization is either T2sp3 or sp3T2. These are the two hybridizations. So one days before S and P, so in this case n-1 day ns and p, and in sp3d2 it is ns np nd. These are the orbitals used. Actually, ligands, they have a pair of electron which they donate to the metal. So now, if let us say we have 5 electrons and ligand is weak, then energy difference is less. So after 3 electrons are arranged in these orbitals, one, two, three. Now 3 electrons are arranged in the lower orbitals only, because the one with low energy are filled first. But now we left with 2 electrons. So there is choice that either they shift to Eg or they get paired in the T2G. So in case of weak ligands, and this energy difference is very, very less. So electron, rather than getting paired, they go in the above orbitals, because in these cases delta O dash is less than P. What is P? Pairing energy. Is energy required to get the electron paired. What is P? Pairing energy. Because when electrons are paired, there is a repulsion, and due to that repulsion, energy is increased. So to get that this electron paired, we have to provide energy, and that paired energy is called energy required to get the electrons paired. Now, if that energy which is required to get the electron paired is less, then they get paired like in strong ligands, because in strong ligands energy difference is more and pairing energy is less. Okay, so energy required to shift the electron in Eg is more, but to get them paired, that is less. Now this delta O first depends upon ligand, and second it depends upon the metal charge. Higher the metal charge, the more is the interaction of the ligand with the metal ion, and therefore more is delta O. So if higher delta O is there, then pairing starts, and then hybridization becomes, because inner d orbital becomes weakened, and therefore hybridization is D2sp3. But in case of weak ligands, as all the d orbitals have one electron, therefore in this case hybridization is sp3d2, because inner d electrons are not involved in hybridization. We need electrons from the outer orbitals. So like if we have fluoride, let us say fluoride is a weak ligand, and cyanide is a strong ligand. Fluoride is a weak ligand, cyanide is a strong ligand. So if we compare Fe F6 3 negative and Fa CN6 3 negative, if we compare these two, in both the cases, what is the oxidation number of iron? That is, what is the oxidation number of iron? Plus 3. So iron 26, its oxidation number, electronic configuration first, that is argon 3d6 4s2. So Fa3 plus, so 3 electrons are removed first from 4s and then from 3d. Keep in mind, see, whenever we write the electronic configuration, we write it like this: 4s2 3d6. And when we form Fe3 plus, so most of the students are committing mistake that they remove the electron from 3d. 4s remains intact. So keep in mind, whenever 3 electrons are removed, these electrons should be removed from 4s first and then from 3d. So 2 electrons are removed first from 4s and 1 electron is removed from 3d. 2 from 4s and 1 from 3d. So this is a wrong exercise. Okay, so you should write like this, that once first electrons are removed from 4s and then from 3d. So in case of Fe3 plus, it is 3d5. Now let us draw the shape of or hybridization of FeF6 3 negative. So in FeF6 3 negative, Fe is in 3 plus form. And what is the nature of fluoride? Fluoride is a weak ligand. So as it is a weak ligand, pairing does not take place. It is 3D, 4S, 4P. So in this case, pairing does not take place. See this one, weak ligand. Therefore, pairing energy is more. So energy required to get the electron paired is more than the energy required to shift the electron to the EG. So therefore electrons are easily transferred to EG and there is no pairing at all. So no pairing takes place because of the nature of fluoride, because it is a weak ligand. And now how many orbitals are required? 6. 6 vacant orbitals are required. So 3D all have one electron, therefore it cannot be used. So we need d orbitals from the outer shell, and therefore 4s, 4p and 4d. So 1 4s, 3 4p and 2 4d. They undergo hybridization sp3d2 and they form coordinate bond with fluoride. So shape is tetrahedral only, sorry, octahedral only. But in this case, shape is octahedral, but hybridization is sp3d2. As outer d orbitals are used, this is called outer orbital complex. And what is the spin? Spin is plus 5/2. That means the 5 electrons are there in the Fe3 plus ion and same number of unpaired electrons are in the complex. So it is called high spin complex. There is no pairing, or high spin complex or spin free complex, because there is no change in the spin on forming the complex. And because of this weak ligand, this complex is not very stable. But now come to FeCN6 3 negative. So in FeCN6 3 negative, you know, cyanide is a strong ligand. So again Fe3 plus, in Fe3 plus, in 3D there are 5 electrons. 4s there is 1 electron. 4p, sorry, in 4s and 4p there is no electron. But cyanide being strong ligand, you know, come to again this picture. As it is a strong ligand, so delta O is greater than P. That's why pairing energy is less, but energy required to shift the electron is more. Therefore, pairing takes place. So, as pairing takes place, it becomes like 1, 2, 3, 4, 5. So, now 2 3D orbitals are vacant, 1 4s, 3 4p. So now inner d orbital is used, hybridization is d2 sp3. So these d2 sp3 hybrid orbitals, they form coordinate bond with cyanide. They form coordinate bond with cyanide. And now again it is shape is same, but ligands are cyanide shape is octahedral only, but because of the cyanide ligands, it is more stable. And again, in this case, there is only one unpaired electron. So comparison of paramagnetic character can be there. See, in this case 5 unpaired electrons, so it is more paramagnetic, but it is less paramagnetic. Both are paramagnetic, but FeCN6 3 negative is less paramagnetic. FeF6 3 negative is more paramagnetic, and here inner orbital is used, so it is called inner orbital complex. Spin is paired, so it is called spin paired complex. Spin inner orbital complex, spin paired complex. Okay. So question is, CO2 plus is easily oxidized in the presence of a strong ligand. So see, CO2 plus is easily oxidized to CO3 plus in the presence of strong ligand because of its higher crystal field energy, which causes pairing of electrons to give inner orbital complexes. So see, pairing of electron takes place, and therefore it gives inner orbital complex because higher charge of the metal favors higher value of delta O, that is called splitting energy. See, this delta O is higher if ligand is strong. Already it is strong, but if charge is higher, then it becomes more than that. That's why it is written that CO2 plus can be easily oxidized to CO3 plus in the presence of a strong ligand. Why? Because of its higher lattice crystal field energy. Because of higher crystal field energy, which is greater than pairing energy, and therefore pairing of the electron takes place, and it gives inner orbital complex. Next, describe the general trends in the following properties of the first series of transition elements. Number of oxidation states exhibited. So you know, first oxidation states increases up to the middle of the series, and then it decreases. Like in the middle of the series, manganese has maximum oxidation number of +7, and then it decreases. First it increases, the number of oxidation states increases up to middle of the series, because in the middle of the series there is maximum number of unpaired electrons, and then it decreases. Next, formation of oxometal ions. So oxometal ions, they are always polyatomic ions with oxygen, like PO2, positive PO, 2 positive Ti, O2 positive even Mn, O4 negative Cr, O4 2 negative Cr, 2O7 2 negative. Okay, so these are the oxo anions. Assign reasons for the following. Copper 1 ion is not known to exist in aqueous solution. Yes, Pranay, what is the reason? What is the reason? Why they are unstable? You are right, but why they are unstable? They are unstable in aqueous solution and undergo disproportionation. But question is why? Because second ionization enthalpy of chromium, though it is large, but second ionization enthalpy of chromium is less. Second ionization enthalpy of copper is less in magnitude than the hydration enthalpy of copper 2 plus. See, copper 1 plus gas and copper 2 plus gas. If we compare And in this case, it is 3D10, it is 3D9. So more stable to less stable it is becoming, and that's why huge amount of energy is required. Second, iron enthalpy of copper is high, but when they interact with water, hydration enthalpy of copper 1 plus is very less, but for copper 2 plus aqueous means when it is hydrated, a huge amount of energy is released, and that energy released is called hydration enthalpy. So hydration enthalpy of copper 2 plus is more than compensated by second iron enthalpy of copper. That's why copper 1 plus ion is unstable, and therefore in aqueous solution it undergoes disproportionation to give copper 2 plus aqueous plus copper solid. Next question, both O2 and F2 stabilize high oxidation states of transition metals, but the ability of oxygen to do so exceeds that of fluorine. It is due to the ability of oxygen to form multiple bonds. Ability of oxygen to stabilize higher oxygen state exceeds that of fluorine because oxygen can form multiple bonds with metal. That's why MnF7 does not exist. Manganese can show +7 oxidation state, but not with fluorine. It can show it with oxygen only. Why? Because oxygen has ability to form multiple bonds. Means only 4 oxygens are required. Only 4 oxygens are required. But in case of fluorine, we need 7 fluorines to show its oxygen state as +7. And it is very difficult to accommodate 7 fluorine around manganese. But it is easier to accommodate 4 oxygens around manganese. And that's why manganese can exhibit +7 oxygen state with oxygen, but not with fluorine. So it is because of ability of the oxygen to form multiple bonds. Next, transition metals and many of their compounds act as good catalysts. What is the reason? We have discussed it. Yes, beta. What is the reason for transition metals and many of their compounds as they act as good catalysts? Transition metals have unpaired electrons. They have vacant d orbital. They can provide surface area. They have ability to form complexes. Okay, and that's why they can form intermediate compounds. And yes, they have variable oxidation state. That is also one of the reasons. So these are the characteristics of transition metals as well as reason for transition metals and their compounds to act as good catalysts. You will write all this. Transition metals generally form colored compounds. Again, because of the presence of unpaired d electrons or partially filled d orbitals to the presence of partially filled d orbitals. That's why they can show dd transition. They can show dd transition in visible region. How do they show? Because they are separated into T2G and EG. So due to dd transition which takes place in the visible region, so complementary color we can see. We can see the complementary color. because white light is absorbed. Visible region, there is the absorption of some color, so complementary color we can see. That's why transition metals generally form colored compounds. If question is there, you can write due to DD transition. Due to DD transition, if you don't want to write like in the visible region and we can see complementary color, it's okay. But just write due to DD transition and because of the presence of unpaired electrons or because of the presence of partially filled d orbitals. That's it. What are the transition elements, and write two characteristics of the transition elements. Just we have discussed what are transition elements. Elements which have partially filled d orbital in its ground state or in any of its oxidation states, that is called a transition element. So what are their characteristics? First, they show variable oxidation states, they form colored ions, they form complex compounds, okay, they can act as good catalysts, okay, these are their characteristics. Write one similarity and one difference between the chemistry of lanthanoids and that of actinoids. So similarity is both lanthanoids and actinoids, they show contraction in size as well as irregularity in their electronic configuration. And what is the difference? Actinoids show wide range of oxidation state. We have seen from +2 to +7, but lanthanoid can show only +2, +3 and +4. Okay, so this, let us write whole similarities and differences. So first, let us write similarity. Similarities between lanthanoid and actinoids. What is the common oxidation state of lanthanoid and actinoid? So keep in mind, both involve the filling of f orbitals. Both the lanthanoids as well as actinoids, they involve the filling of f orbitals. So first similarity you can write that both lanthanoid and actinoids involve filling of f orbitals. Second, both show mainly an oxidation state of +3. Next, both are electropositive and very reactive. Both exhibit magnetic and spectral properties. Next, actinoids exhibit actinoid contraction just like lanthanoid exhibit lanthanoid contraction. So these are similarity. between lanthanoids and actinoids. Both involve filling of f orbitals, both show mainly oxidation state of +3, both are electropositive and reactive, both exhibit magnetic and spectral properties, both exhibit contraction. Actinoids show actinoid contraction, lanthanoids show lanthanoid contraction. Now let us write the differences. So lanthanoids, actinoids. First, common oxidation state is +3, but besides +3 oxidation state, they show, yes, tell me, they show +2 and +4 oxidation stage in few cases, only in few cases. Now come to actinoids. In actinoids, besides +3 oxidation state, they show higher oxidation state of +4, +5, +6 and +7. Okay, even +7. Second, lanthanoids. In lanthanoids, most of their ions are colorless. Most of their ions are colorless. But in actinoids, most of their ions are colored. Most of their ions are colored. Then lanthanoids, they have less tendency to form complex, or we can say they have less tendency towards complex formation. But in actinoids, they have greater tendency to form complexes, or we can say towards complex formation. Next, lanthanoids, their lanthanide compounds are less basic, but actinoid compounds are more basic because actinoids are larger in size than lanthanoids. So actinoid compounds are more basic. Next, lanthanoids, they do not form complex, oxocation. They do not form oxo ions, but actinoids, they form oxocations. For example, UO2 positive, PuO2 2 positive, UO2 2 positive. Here, lanthanoids, they are non-reactive except promethium. So, except promethium, they are non-radioactive. But all the actinoids, they are radioactive. Last point of difference is in lanthanoids, their magnetic properties can be explained easily. Can be explained but in case of actinoids, their magnetic properties cannot be explained easily. Why? Because they are more complex. Okay, these are the difference and similarities between lanthanoids and actinoids. Next is what is meant by disproportionation. Give an example of disproportionation reaction in aqueous solution. So example is, you know better, just we have done just now. What is that? That copper 1 plus. Disproportionate reaction, what is that? In a disproportionation reaction, you know, the element of a compound, you can write element of a compound undergoes self oxidation as well as self reduction and forming two different compounds. For example, means there is ox means oxidation and reduction takes place simultaneously. So one of the, like in this case, see, copper 1 plus aqueous. So copper 1 plus aqueous is oxidized to copper 2 plus aqueous, and copper 1 plus aqueous is reduced to copper solid. So it is one of the disproportionation reaction. One more example is provided by manganese. MnO4 2 negative. So MnO4 2 negative in acidic medium, it changes into MnO4 1 negative and MnO2. So just balance it. It is like this. So in MnO4 2 negative, oxidation number of manganese is +6. In case of MnO4 negative, it is +7, the change of 1, and MnO2 it is +4, so change is of 2. That's why it should be 2 and it is written as 3. 3 MnO4 2 negative plus 4H plus ion to give 2 MnO4 negative plus MnO2 plus 2H2O. How do we balance it? See, MnO4 2 negative, first it gives MnO4 1 negative, and MnO4 1 negative, it gives MnO2. So just balance it in acidic medium. MnO4 negative to MnO4 2 negative to Mn1 negative, MnO4 2 negative to MnO2. So in first case, atoms, all the atoms are balanced, only charge. So we add 1 electron here. In this case, manganese is 1, 4 oxygens, 2 oxygen. So we add 2H2O on the side deficient of oxygen, 4H plus on the opposite side, and plus 2 electron. And just multiplied by 2 so that electrons are cancelled. So it becomes 2 MnO4 2 negative and 1. So total 3 MnO4 2 negative plus 4H plus aqueous to give 2 MnO4 1 negative aqueous plus MnO2 solid plus 2H2O liquid. That's it. So this is one of the disproportionation reaction, because in this reaction MnO4 1 negative is oxidized to MnO4 negative and other is reduced to MnO2. Suggest reasons for the following features of transition metal chemistry. First is transition metal and their compounds are usually paramagnetic. Why are they paramagnetic? Because they have unpaired electrons. Transition metals and their compounds are usually paramagnetic because they have unpaired electrons in the transition metals and their compounds, they are paramagnetic because of the presence of unpaired electrons in the partially filled d orbitals. Next, transition metal exhibit variable oxidation state. Why they show variable oxidation state? Yes, beta. Why are they showing variable oxidation state? Because of N-1 day and Ns, energy of N-1 day and Ns subshells is almost equal. Therefore, electrons of both subshells can participate in bonding, and that's why they can show variable oxidation states. So why they are showing variable oxidation state? Because of the participation of N-1 d and Ns electrons. Okay. Is it okay, beta? That's why manganese can show +2 to +7, because in manganese it is 3d5 4s2. So 4s as well as 3d, both are treated as valence orbitals. Therefore, electrons of 4s and 3d are involved in bonding. So manganese can show oxidation state from +2 to +7. Yes, beta. Is it okay? Okay, wait. So transition metals exhibit variable oxidation state because of the participation of n-1d and ns electrons, because they have almost equal energy. That's all for the day. Yes, but any doubt? And so, yes, beta. So these are questions from 21 to 30. So do these questions as early as possible. And at the same time, we are covering whole NCERT of 11th and 12th, their concept, their examples in text, exercise questions. And after doing all this, we will do NEET and JEE questions of each and every chapter. And this is all free of cost. So support my free education drive. Just share my channel with all your friends, your classmates, so that our community will grow and we have million subscriber in a short period. That is my aim, because I need that my channel will reach each and every one, so that all will be benefited with this free education drive. Thank you so much for watching this video. Do share, and if you like this video, do like, and at the same time ask your friends to join. And though it is free, but I will cover each and every topic. I will not left any stone unturned, so that you can qualify CBSE, NCERT exam of any state board with full marks and good marks in NEET and JEE exams. That is my aim. God bless you all, and thank you very much. Support my channel, support me as an individual. I am nothing without your support. Thank you so much, all of you.